Let's think about annuities, loans, and mortgages. Do two examples and derive some general formulas. The first one is one that we've basically done, but I want to put it in terms of the book's notation. Suppose we invest $2,000 each year at 9% annual interest, and for simplicity, we're going to have it compounded annually for 30 years. How much do I have at the end of that time? Okay. Well, one way to think about that is to think about all the individual payments as going into separate accounts. And we can actually, I find it easier to think about the last payment you just put in. The very last payment, right at the end of 30 years, you don't get any interest on at all. So it's just $2,000. The one the year before, you get the $2,000 plus 9% interest, and we know that that amounts to multiplying by 1.09. The one we put in 2 years ago, it's gotten 2 years worth of interest. So it's just basically, regular compound interest, $2,000 for 2 years. All the way up to the one we put in 29 years ago. The first year, it's earned 29 years worth of interest, so you get 2,000 times 1.09 to the 29. Now you might say, well, is there one with 30 years? This is basically saying they'll give us the interest and then we put in the payment. If we did it the other way, it'd be slightly different. This one works out the nicest way, though. And this is a geometric series. The first term, it's a finite geometric sequence, a sum of a finite geometric sequence, rather. The first term is 2,000. The ratio is 1.09, so we get 1 minus 1.09. I like to put that in parentheses, especially for what follows. To the, remember, it's the next exponent, the next power over 30, and then 1 minus 1.09. And that's a little annoying because both top and bottom are negative, and so we're just going to flip them and simplify the bottom. We get 1.09 to the 30th minus 1, and then over, it's just the interest rate that shows up here, because this is 1 plus the interest rate, and then we end up subtracting 1 when we flip it. Okay. So in general, what we do is we call this regular payment, it's like a rental kind of, something paid every month, so we call it the periodic rent. And that's called R for rent. And okay, yeah, why did we use R when we had R for something else? The little r, big R, it's confusing, I know. And then the interest rate is going to be I. That's not imaginary, although it's interesting if you think about what happens when you let it be imaginary. And the number of payment or compounding periods, let's say that's N. Okay. So notice there's 30 total payments here. And that's the N. So this is N minus 1. But the N does show up here. Then we call the final amount we have, the total, or amount sub final. We can just look and see what we did. Okay, it's always going to be that periodic rent times, what was this? This was 1 plus the interest rate to the N, that's the number of periods, and then divided by the interest rate. So it's a funky looking formula, but we really know where it came from. It really came from just summing up all these regular compound interest things and then using the wonderful shortcut we have for a sum of a geometric sequence. Okay, and in this case, that's going to be, well, let's see. Before we calculate the number numerically, let's see how much money you put in. $2,000 a year for 30 years, that's $60,000. So you should have at least $60,000, somewhat more. And the question is how much more? 273 almost, so $272,620-ish. Okay, that's a lot more, and that's the power of a pretty decent interest rate. That's the kind of interest rate that somebody would have gotten in the stock market, say, from about 1970 to 2000. Actually, that's underperforms the stock market, so that's pretty good. Okay. Now, the flip side of that, instead of saving money and earning interest, is borrowing money for a loan and paying interest. But it turns out to be a very similar formula. The book has a certain derivation of this that I find a little, I just think it's probably going to be a little obscure. So what I'm going to do here is a little different. So here's the situation. We're buying a house. We want to pay a certain amount of down payment, but usually you don't buy a house in cash. So we're going to borrow a substantial amount of money, $150,000 at 7%. Annual interest, and for simplicity, we're going to have it compounded annually. Usually it would be monthly, and we could redo it with a little bit more accuracy, but it's not a big deal. And let's say it's a term of 30 years. So what that means is that they're going to set it up so you pay a regular payment. Usually that'd be monthly, but for simplicity, we're going to do it yearly here. And let's say you pay once a year, and it's supposed to be the same amount, so it's this regular payment stream. But it's supposed to be set up so you end up paying it off exactly at 30 years. And now, so what is that yearly payment? And that's going to be the analog of R. That's going to be the periodic rent. And then how much do you end up paying in total? Well, that's interesting. Okay, probably more than $150,000. And it's going to be interesting to see how much more. So here's the way I like to do it. Here's the progress of the balance of the loan with time. Year 0, you haven't started the process. You owe $150,000. Year 1, you owe $150,000, but times 1.07. So they've charged you interest on the amount, but then you've paid off your monthly rent. Now, we don't know that. Well, that's where we put it in as a letter, and we'll figure it out later. So that's, if we knew the monthly rent, that's what we would have. It's okay that we don't know yet. Now, year 2, you're going to take that entire expression and you're going to get 1.07 interest charge on that. But then you're going to also knock it down by paying again. Okay. Now, really important that there's a slightly better way to write that. 150,000 times 1.07 squared minus, and then there's an R in the other two things. And it's 1 plus 1.07. That should maybe start to look a little familiar. Okay. Year 3, we're going to take that entire amount, put it in parentheses. That's what they're charging us interest on. And then we knock it down with another monthly rent. Okay. Looks a little intimidating, but here's where we're going to start to see there's actually a fairly simple pattern. We're going to get 100, when we distribute in this 1.07, we're going to get 150,000 times 1.07 cubed. Notice that this thing, 150 times 1.07, 1.07 squared, 1.7 cubed, that's just ordinary compound interest. And then let's see. We've got an R in everything else. This is just R times 1. Here, you've got an R times 1 times 1.07. Okay, 1.07. And then R times 1.07 times 1.07. Ooh, 1.07 squared. Ah, well, let me put that in parentheses because I like to do that. Aha! Okay, I think we can guess what's going to happen in year 4. We're going to have $150,000 times 1.07 to the 4th power. But then we're going to have that R. We paid it once without any benefit of reducing the interest paid. We paid it a year ago, and that gets an extra benefit because we don't have to pay interest on the R that we took out a year ago. We get an even more extra benefit. Notice even though these are pluses, it's all being subtracted. And this is an amount we want to be small because this is what we owe. The stuff we paid 2 years ago, we haven't had to pay interest on that for 2 years. So that's why this number is there. And the stuff we did 3 years ago, we haven't had to pay interest on that for 3 years. So that's really another explanation why we get this funky series after R. Okay. After year N, it's going to be very similar. And this is about where we got to. We had a problem like this where I gave you the R as a known quantity. And with some difficulty, we got to something like this with different numbers. But we got this pattern. We got regular interest minus the payment times the geometric. Okay, so this is going to be to the nth power. And then this is going to be plus dot, 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 and then 1.07 to the n minus 1 power. And hey, look, that's exactly what we like to see. That part is exactly our geometric series. It's really exactly what we got up here. Okay? So, after year 30, we can just plug in n equals 30. And this is going to be 29. Okay. And the first task, well, what is this supposed to be at year 30? This is where we finally get the punchline. This is all predicated on knowing R. Otherwise, these things are fairly useless. Except right at year 30, what do we know about the amount we're supposed to owe? Think about that for a second. You might even want to pause the video. How much are we supposed to owe after exactly 30 years? It's supposed to be 0. Because it's supposed to be a 30-year mortgage. And now I can solve for R. Okay, so R is just going to be, move it over and divide 150,000 times 1.07 to the 30th over this big sum all the way up to 1.07 to the 29th. Now, we have a shortcut for that, the bottom sum. Okay, so let me just write the top again. 1.07 to the 30th. And then the shortcut is itself a fraction, so that's going to look a little bit complicated. It is 1 minus 1.07 to the 30th. Hey, that's the same power. Interesting. Over 1 minus 1.07. Okay. Well, let's simplify the bottom first, because we know that simplifies a little bit. We can flip the order because they're both negative. And then this just becomes 0.07 on the bottom, and this becomes 1.07 to the 30th minus 1. So it's going to be a little tiny bit of algebra here. How do you divide by a fraction? You multiply by the reciprocal. Okay, and so we're going to multiply by 0.07 over 1.07 to the 30th minus 1. That's not a horribly bad answer, but there's a little bit better way to do it. Let's combine the 150,000 and the 0.07 together. 0.07, okay. And then we want to take advantage of that, the fact these are the same number. You don't have to calculate that twice, okay? So I'm just going to divide top and bottom by 1.07 to the 30th. So that makes this go away from the top. Dividing this by itself gives us a 1. And then I'm going to get 1 over 1.07 to the 30th. There's a nice way to write that. It's 1.07 to the negative 30th. So just a little algebra, dividing top and bottom by 1.07 to the 30th and using negative exponents. Okay. Let me go ahead and put down the official terminology for this. We've got interest rate, that's the 0.07. The loan amount we're going to call AP. Just to agree with the book, they relate this to what's called present value of an annuity. I don't know if we're going to do that, but we're just going to call the loan amount AP. And then this is just 1 minus good old 1 plus I to the minus n now. So that's a kind of a funky thing. We get a minus n. That was because of this funky cancellation here. Okay. And that is the monthly rent, or actually this is the yearly payment for this example on this loan. So let's calculate that numerically. 12,088. Okay. Now, if you split that up into monthly, and again, this isn't going to be quite exact because they would probably compound it monthly as well. That's going to be 1208 over 12, and that's going to be just a little over $1,000. 1,007.30 cents. It's kind of getting a little awkward here. Sorry. There we go. Okay. Over $1,000 every month for 30 years. Okay. Now, what's the total payments? Well, we just multiply this, the 12,088, by 30. Let's put it down here. Total repayment is 30 times 12,088. And that's going to be $362,640. Put it up here. $362,640. That's a lot more than $150,000. It's over double. And so a 30-year mortgage at even 7% interest, which isn't exorbitant by historical standards, you end up paying a lot of money. But unless you have $150,000 cash that you want to spend and not have, that's pretty much how people have to do it. But that's why you want to be a landlord. That's why you want to be a mortgage company. Make a pretty good amount of money. Okay. So here we finally got a nice formula, which you don't have to rederive this thing every time, that if you know the amount of the loan, we'll call that A sub P, and the interest rate and the term of the loan, that gives you your periodic rent.